In this video, we're going to identify and analyze two different trends that occur between different types of solutes and what happens to their molar solubility as the temperature is increased or decreased. Now, depending on what our solute is, there are two different trends that we can see. For example, if our solute is an ionic solid, for example, sodium nitrate, potassium nitrate, ammonium chloride, potassium chloride, sodium chloride, etc., are all examples of ionic solids, and as their temperature increases, their molar solubility also increases corresponding to temperature, so we seem to have a direct relationship between the two. However, if we take a look at examples of gases, for example, ammonia, hydrogen chloride gas, sulfur dioxide, we see that the opposite occurs, where as temperature increases, their molar solubility decreases, meaning that solubility and temperature seem to be inversely related for gases. Now, why does this difference exist? Well, let's consider the dissociation of one of the ionic solids on the data table, potassium nitrate. Now, if we remember why dynamic equilibrium systems form, we know that they form because enthalpy and entropy favor opposite sides of the reaction. Now, in order for us to identify where delta H is in this reaction, we need to look at how entropy favors this reaction first, because we're not given where delta H is. Now, in this case, we can conclude that entropy must favor the products. If we remember basic principles of entropy, we know that as the number of particles increases, the entropy will increase, and our products have two different particles where the reactants only have one. We also see that the state of matter of the products is aqueous, which is a more disordered state of matter than an organized ionic solid. So therefore, if entropy favors the creation of products and we have an equilibrium system form, that must mean that enthalpy must favor the formation of the reactants, and therefore we would expect that delta H exists in the reactants. This is not always true, and we'll see exceptions of this later on, but if we assume that delta H is in the reactants here, an increase in temperature means that, remember that both forward and reverse reaction rates increase when temperature increases, but only one side has delta H, meaning that when the forward reaction happens, delta H, this extra energy is produced, which therefore increases the temperature and feeds back into the forward reaction rate like this, causing the equilibrium to shift to the products. Therefore, if we assume that delta H is in the reactants, a temperature increase will disproportionately affect the forward reaction more, and therefore a temperature increase will lead in more products being formed, meaning that the ion concentrations of potassium and nitrate should increase, meaning that more of it should be able to dissolve. And this explains why ionic solids generally have positive trends when it comes to increases in temperature, showing that increases in solubility seem directly related to it, and this relationship between enthalpy and entropy seems to consistently explain why. Now, does this also work with gases? Well, let's start by considering the same idea of finding out which side entropy favors. Now here we can't look at gas particles because we don't have a dissociation reaction here. We just have ammonia in gas form and ammonia in aqueous form. And we know that gases have a higher entropy than aqueous particles do because gases have complete freedom of movement, whereas aqueous particles are trapped within the solvent of the solution. So if entropy is what actually favors the reactants in this case, because again, gaseous ammonia has a higher entropy than aqueous ammonia does, and we get an equilibrium that forms, that means that the product side must contain delta H so that enthalpy favors the opposite side as entropy does. And if we assume that delta H is here, something interesting happens when we increase temperature. So if we increase temperature, that means, again, both forward and reverse reactions rates increase, meaning that we get more energy generated from the exothermic reaction, and this extra energy increases the temperature further and feeds back into the reverse reaction, therefore pushing the equilibrium towards the reactants, which happens to be towards the gas form of NH3, meaning that if this is true, a temperature increase, because it pushes the reaction in the direction of the gas form, this would cause the concentration of the aqueous form to decrease, meaning that as temperature increases, less gas dissolves per unit of volume because more of it is being pushed in the generation of the gas form. And this would explain why there seems to be an inverse relationship between temperature increases and molar solubility of gases. Now, as we can see, although these trends are generally true, there do seem to be some exceptions. So if we take a look at this compound here, cerium sulfate, this compound here, cerium, is, I believe, a transition metal of some kind, fairly low on the periodic table. But the point is that this is clearly an ionic solid, and we see that it behaves in the opposite way as solubility trends with other ionic solids. So the short and simple answer about why these exceptions occur is that entropy is not always completely predictable, which is why we need to look at the standard molar entropy in order to be able to truly predict which side of the reaction is favored by entropy. But nevertheless, the general trend of ionic solid solubility increasing as temperature increases, and the opposite for gases, holds generally true. In the next series of videos, we're going to expand upon this trend and look at overall patterns that occur due to Le Chatelier's principle pertaining to solubility equilibrium.